Namaste and welcome to this last lecture on linear algebra through geometry. We are not going to do anything great here. We just thought we will give a summary of the entire course that we have had, because this was a course which was completely on a different format we had, in the sense like we had a lot of visualizations and geometrical approach to this ideas of linear algebra. So, I hope all of you had a good time in understanding the concepts and understanding the ideas and the insights and intuitions that we have given. I think if you look at the course overall, we started off with an introduction where we just said, okay, we kind of created a curiosity in you all, saying that look, these are the places where linear algebra is actually there, like which we have not looked at. And then we started looking at solving systems of equations like in 2 unknowns, 3 unknowns and n unknowns and m equations and stuff. So, we basically had 2 weeks of that, and then we started off with the 2-dimensional geometry, where we looked at lines, vectors, then points, coordinate systems and other things. We also started looking at matrices as transformations, or transformations we looked at in terms of matrices. And we looked at various linear transformations like rotation, reflection and shear, scaling and a whole lot of stuff. Once we did that, we actually had certain intuitions there. We looked at let us say the rotations and reflections and stuff, and then we also looked at those set of vectors which are kind of what would you say, they are their orientation does not change upon application of this transformation. So, we call them as the eigenvectors, and they basically get scaled. So, the scaling factor was called as the eigenvalue, and then we figured out that okay, there are a few things which kind of were what would I say, not I mean, if you look at the eigenvalues eigenvectors problem, you had a real matrix, and we said that okay, for this real matrix you actually have a complex eigenvalue and a complex eigenvector. I mean, that was quite surprising. So, what we did is like surprising in the sense like we were looking at everything real vectors, and then transformations to be linear transformations are real, and then suddenly we come out saying that look at the roots of this quadratic equation that you have, they are complex, and then in turn therefore you get the eigenvectors to be complex eigenvectors and so on. And then what we did is okay, fine, no, there seems to be something here, let us go to 3 dimension and see what happens. And in 3 dimension we looked at the idea of the determinant of a matrix as a volume of the parallelepiped, which in 2 dimension we looked at the determinant of a 2 by 2 matrix as the area of a parallelogram. And we went on to look at again the same what would you call linear transformations, but before that we actually looked at another interesting idea of of the cross product. The cross product of 2 vectors being another vector which is orthogonal to the plane containing the 2 vectors. So, that is what we looked at, and in fact when we looked at the cross product, we said that okay, if you have 2 vectors, that means you have that a system of 2 equations in 3 unknowns with the right hand side equal to 0, the homogeneous system of equation Ax equal to 0 with just 2 equations and 3 unknowns. We said that the solution to this system of equation was actually the cross product of the 2 vectors, which were like the coefficient matrix, the coefficients, the vector containing the coefficients we had. So, that is something which we saw, and post that we actually looked at many other interesting stuff. We looked at interpreting the solutions to the system of equations and so on, and then we looked at Gaussian elimination method and then LU decomposition, and we said that okay, there could be a problem where we may not have a solution. So, in which case what do? If we may have a system of linear equations wherein which we may not have solutions to exist. What do we do in that case? And that is exactly we got into where we got into the idea of least squared solutions. We said that okay, this is the destination that we actually wanted to go, but that is not the destination where we can go with the kind of vehicle that we have. So, what we said is go as close as possible to that exact destination that you want. That means you have a destination and you could go reach only to a particular point, so that the distance between the original destination and the actual destination that you could go, the square difference basically or that is basically what we call as the squared error, and the squared error was minimum. So, this is something which we looked at, and that is exactly where we got the idea of least squared solutions. Post that, what we did is, like we said, okay, we have understood everything in 2 dimension, we have understood in 3 dimension. Now it is time for us to generalize things. So, what we did is we started looking at the vector spaces, the idea of vector spaces. Vector spaces was I mean the idea of vectors was not necessarily restricted to the school idea of vectors having what we say a magnitude and a direction. In fact, we said that okay, a set of matrices could be a vector space. That means every matrix could be a vector is what we said. A set of polynomials could be a vector space under certain operations that we already defined. That means vector addition and scalar multiplication and the existence of the 0 vector and so on. So, this is something which we saw, and we actually looked at a lot of examples of vector spaces, and we also said okay, this vector space is going to be a quite larger entity. So, what we said is let us start looking at subsets of vector spaces which are vector spaces themselves. That means you have a sub collection of the vector space, and wherein which the ideas of vector addition and the scalar multiplication and the existence of 0 vector is guaranteed. You call them to be the vector subspace, and we figured out that in 2 dimension the vector subspaces could be the entire 2 dimensional plane, the xy plane that we have, or a line passing through the origin could be a vector subspace we said, and then the set containing the origin alone we called that to be the trivial vector subspace or the vector space. In 3 dimension these boil down to the ideas of planes passing through the origin, lines passing through the origin, of course entire R3 and the 0 vector, the set containing the 0 vector in 3 dimension. These were all the what would you call the vector subspaces in different dimensions that we had. We also looked at how do we generate these vector spaces. We actually looked at the idea of what are called as bases. The basis is nothing but a set of linearly independent vectors which will span the entire vector space or the vector subspace, and we defined what is linearly independent. We had actually followed this idea of linear independence right from our 2 dimension onwards, where we said that okay, any 2 vectors in 2 different directions are going to be linearly independent, but then we wanted to formalize it mathematically. We said that if you have non-zero vectors, a collection of non-zero vectors, then the only way in which the linear combination of these non-zero vectors that will give the 0 vector is basically having all the coefficients to be 0. If you take the linear combinations, each of the vector gets scaled by certain scalars, and the only way in which you can get the 0 vector in this case is basically by making all the scalars 0, right. That is what we had. And so basis we said that it is going to be a collection of linearly independent vectors. And we also had another definition where we said that the number of vectors that are there in the basis correspond to the dimension of the vector space, and in fact we also said that every vector space can have infinitely many bases, and the only thing is like all the bases that you have, let B1, B2, Bn be the basis for different bases for a vector space. We said that each of these bases will contain the same number of linearly independent vectors corresponding to the dimension of the vector space or the vector subspace. And along that line we also looked at the most important stuff, where we had the trivial vector space which contains only the 0 vector. So, in this vector space the only vector that is present is the 0 vector. Unfortunately, any set that contains a 0 vector is considered a linearly dependent set. So, how do we even talk about basis here? On that note we said that okay, remove the dependency there, that means remove the 0 vector, what you get is basically an empty set, and we said that the empty set is the basis for the vector space containing only the 0 vector, and that means the basis, the vector space which contains only the 0 vector is basically called as the 0 dimensional vector subspace or the vector space. So, this is something which we saw, and once we started going getting the ideas of our vector space, basis, subspaces, everything correct, then we said that okay, look, when we tried to solve system of equations we found certain interesting things. What did we find? We find that okay, if you look at the homogeneous system of equations in 2 unknowns or 3 unknowns or whatever that you see, you could have only the trivial solution to be the solution for this, which means only the 0 the values x1 is equal to 0, x2 is equal to 0, etc., xn is equal to 0 is the solution for a homogeneous system of equation. This could be one possibility. That means the solution set to the homogeneous system of equation is basically the single solution which contains all components to be 0, and we found that a set which contains only the 0 vector was actually a vector space, and therefore we were actually looking at the collection of vectors which get into which form the solution to Ax equal to 0 or the homogeneous system of equations, and we call that to be the null space of the matrix that we were working with. And we identified that there are 4 fundamental subspaces associated with a given matrix. One is the null space of the matrix, then we have the null space of the transpose of the matrix, then we had the column space of the matrix, and we had the column space of the matrix transpose, which was also the row space of the matrix A. This is something which we saw, and we also gave another name for this column space. The column space was also called as the range of the matrix, so we had that. So we associated 4 fundamental subspaces with a given matrix, 2 of them on the what we call 2 of them to be the subspaces of Rn, the n dimensional vector space, and 2 of them to be the subspaces of the m dimensional subspace. So this is m dimensional vector space. So this is something which we looked at, and we said that okay, I mean these are the 4 fundamental subspaces which are always associated with the matrix, but there could be other subspaces associated with the matrix, and that is where we got into the idea of this I mean we even looked at before that we even looked at the idea of orthogonal complement subspace. We were looking at the set of vectors which are orthogonal to a given set of a vector or given vector space, and that is what we call as the orthogonal complement. And in that sense we said that okay, the null space of the matrix A and the row space of the matrix A or the column space of A transpose, they are orthogonal complements of each other, and these 2 are subspaces on the Rn side. That means these 2 are subspaces of the n dimensional vector space, and on the other side, that means on the m dimensional vector space, we said that the column space of the matrix A and the null space of the matrix A transpose are orthogonal complements of each other. And in fact we also established this idea of a rank nullity theorem, which said that the rank of the matrix is basically what we call as the dimension of the column space of the matrix, and we had the nullity which was basically the dimension of the null space of the matrix. So we said that rank plus nullity is equal to number of columns, which we saw in previously, like when we solved system of equations. We said that okay, the number of pivot variables plus the number of free variables is equal to the total number of columns of the matrix, and that is something which is in the vector space format. When we looked at matrix as linear transformations, we could actually say that the rank plus nullity is equal to the number of columns. So that is something which we understood, and in addition to this we were also looking at the idea of what are called as invariant subspaces. I mean we were basically looking at square matrices for which or square matrices, basically we are looking at linear transformations for which there could be certain vectors which do not get reoriented at all. That means if you do A into x, that means if you try to transform a vector x using a linear transformation A, the resultant is going to be just the scaled version of the vector x. So you are going to get Ax equal to lambda x, and that is precisely what we called as the eigenvectors, and lambda were called as the eigenvalues. Now associated with every eigenvalue you have an eigenspace or the invariant subspace. We had actually looked at all that, and but what we found was like not necessarily that you may have matrices to have real eigenvalues and real eigenvectors, and therefore we started looking at certain special. We also said that okay, first of all in order to find out the eigenvalues you basically have to look at the characteristic equation of the matrix, which is determinant of A minus lambda I is equal to 0. There are 2-3 things that we commented here. We said that look, determinant is defined only for square matrices, it is not even defined for rectangular matrices, and even if we have the determinant for a square matrix, we found that okay, there may not be sufficient number of eigenvectors, which means when we try to diagonalize the matrix it may not be possible. So that is where we got into the idea of algebraic multiplicity and geometric multiplicity of the eigenvalues and of the eigenvalues. So we said that the number of times an eigenvalue repeats is basically called the algebraic multiplicity, and the number of eigenvectors associated with every eigenvalue is what we call as the geometric multiplicity. So, this is something which we saw. And we also saw that with the help of eigenvalues and eigenvectors you could actually diagonalize a matrix. We said A is equal to P d P inverse, where P is the matrix which contained all the eigenvectors and D is the matrix which contained the eigenvalues, and D is also a diagonal matrix. And if there are insufficient number of eigenvectors you can't even do this diagonalization. So, there was another problem that we faced. Once we did that, we wanted to understand how does a matrix transform a vector to give you another vector. In general, suppose you say Ax is equal to B, we wanted to figure out what does this Ax equal to B actually mean. How do I get B? Mathematically I can figure out what they are, but geometrically we want to find out what is A doing to X so that you get this vector B. And that is exactly where we got into the idea of real symmetric matrices. We said that okay, we were not able to get a clear understanding of what happens when you do Ax is equal to B, but then when we looked at let us say real symmetric matrices, we got a clue as to what is happening. So, what we did was we looked at real symmetric matrices with distinct eigenvalues, and we said that the eigenvectors corresponding to these distinct eigenvalues are orthogonal to each other, and therefore they would form another basis. So, what we said is the action of the matrix A on the vector x is to basically project the vector x onto orthogonal axis, scale the projections, basically you get the linear combination of this projections. So, that is basically what we had. And in fact, the other interpretation that we had was, since the matrices the vectors are orthogonal, we had this u transpose plus v transpose and so on, where u and v were the eigenvectors which are orthogonal to each other corresponding to the distinct eigenvalues of a real symmetric matrix. We had that, and interestingly what we found was this u transpose v transpose were all rank 1 square matrices of whatever dimension that we took for u, the number of the vectors. Basically if u is a 3 component vector, u transpose is going to give you a 3 by 3 matrix of rank 1, and v transpose is going to give you another 3 by 3 matrix of rank 1, and so on. So, then what we said, this decomposition that you have, the sum decomposition or the sum form of the eigenvalues, eigen decomposition, we said that this was equivalent, or this was actually a basis expansion for matrices. You want to generate a matrix A, here you have, so you use the eigenvectors, you generate matrices using the outer product, and then you use the different scalars, you end up getting different matrices. So, basically we said that linear combination of matrices, and these matrices that we had, u transpose, v transpose, w transpose, whatever they have corresponding to the eigenvectors, orthogonal eigenvectors of real symmetric matrices, we figured out these could form the basis for the n by n square matrices, real symmetric matrices, the vector space of real n by n matrices. So, what we did, you change the scalars, you get a different matrix. Now, there we had another question. We said that look, okay, this is fine, like you can get an eigen decomposition for square matrices, you can probably even get eigen decomposition, a subclass of this which we took as real symmetric matrices, we were able to get that. But most of the real world problems that we have are typically rectangular matrices. You either have more number of rows, or probably you have more number of variables, one of these two happens, in which case how do we tackle this, and that is exactly where we got into the idea of getting a symmetric cousin of this matrix A. What do we mean by that? We say that you have a matrix A, you try to find out A transpose A or A transpose, that becomes a real symmetric matrix, and now all the properties of real symmetric matrix follows. So, what we did was we basically looked at the eigen decomposition of this A transpose A or A transpose whatever that we had, and that is exactly where we got into the idea of singular value decomposition. What is interesting we found was like whether eigen decomposition for a matrix exists or not, singular value decomposition always exists, which means singular value decomposition is something which is very native to the matrix, is what we figure out. The singular values are basically native to the matrix, which are always there. So, we looked at the idea of singular value decomposition from the product form and from the sum form. Product form was u sigma v transpose, which was equivalently PDP transpose or PDP inverse in square matrices case. Here we had u sigma v transpose. We also defined something called as the pseudo inverse in this case, because inverse is defined for square non-singular matrices, and I mean non-singular matrices. Inverse is also defined only for square matrices, we already know that. And in case of rectangular matrices, the determinant is not defined, and hence inverse is also not defined. So in which case what do we do with that? So that is exactly where we got into this cousin of this matrix A, which is basically A transpose A and A transpose. And what is interesting if you see is the rank of A, the rank of A transpose, the rank of A transpose A, and the rank of A transpose, they are all the same, which means all these 4 matrices are going to convey the same information as as any of these 4 matrices, as the matrix A. We could take it that way in terms of the rank, I mean nothing more. In terms of the rank, A transpose A transpose, A transpose and A, all 4 of them are going to convey the same information. That is exactly what we looked at. So we also looked at the singular value decomposition as sigma I, let us say the singular values into ui vi transpose. You basically summation, do a summation from r I is equal to 1 to r. Basically you try to express a rank R matrix as a linear combination of R rank 1 matrices, and in fact what we figured out was singular value decomposition is also another basis expansion, in fact orthonormal basis expansion for matrices. In fact that is another way to generate rectangular matrices, is what we saw. And subsequent to that we also looked at the idea of quadratic forms, and then what is the advantage of, why is the need for quadratic forms and stuff. We said that if you look at optimization problems, single variable optimization is always like kind of easy, where you understand that if you have y is equal to f of x, you can find out dy by dx and d square y by dx square, and you can equate dy by dx to be equal to 0 and find the point at which you have a maxima or minima based on the sign of d square y by dx square. So he said that if d square y by dx square is going to be positive, you have a minima, d square y by dx square is negative, you have a maxima, and we are able to get that. But most of our classical problems or the real life problems involve multiple variables, and we need to get the point where we basically look for optimizing multivariable optimization problems, solving multivariable optimization problems, in which case these quadratic forms comes into picture. We said that you take the you get, probably in another optimization course you would probably see that you look at the Jacobian, you look at the gradient, and then look at the Hessian matrix and stuff. We say that if x transpose Ax is going to be greater than 0, then you say that the matrix is positive definite. If x transpose Ax is greater than or equal to 0, then you say that the matrix is positive semi-definite. If x transpose Ax is less than 0, you say it is negative definite, and less than or equal to 0 you say it is negative semi-definite. So we had this definitions, and we say that you have a maxima or minima whenever you have a minima whenever this x transpose Ax is, we had this ideas like you will see that it is related to Hessian. So we looked at quadratic forms from the perspective, and we also know that a lot of things is used in machine learning, all these ideas. And towards the end of our course we also looked at some amazing applications of linear algebra. Probably we looked at the idea of Fourier transform, we looked at JPEG compression, we looked at how does a CT scanner work, we looked at how does even the mobile phone work, like generating tones. So we were looking at this as an eigenvalue eigenvector problems, and we looked at a whole bunch of interesting applications there. And with that the course basically came to an end. We looked at most important thing, we looked at the idea of Fourier transform, which is the bread and butter for any of these electronics and communication engineering or communication engineers as such. So we did a whole lot of things in this course, and you would have seen that most of the lectures that we had were accompanied by visualizations. We tried giving as many visualizations as possible for as many concepts as possible, but in case we were like lacking, probably we will try to improve on that in the next course or the next iteration of this course. So I thank all the participants for having enrolled in this course. I hope this course was a very interesting one. Probably you got a lot of insights, and I am quite sure there were a lot of mistakes both in terms of assignments and somewhere the content delivery also. We set it right. We try to minimize our error. Basically that is also another optimization problem that we are trying to do. We have tried to minimize our error as much as possible, and I think as a whole this course I hope it had given a different perspective to your understanding of linear algebra. On that note, I thank Gaurav Hegde, who was solely responsible for this entire visualization. So he did it from scratch. All the visualizations that you have had, it was done by our teaching associate, Mr. Gaurav Hegde. He did an amazing job, I guess. I'm quite sure some of the feedback that we got during the live sessions that we had spoke very high about the visualizations. Probably we will try to do more courses based on these visualizations, with the help of visualizations. I also thank my co-instructors, Dr. Ashok Rao and Mr. M. Krishna Kumar, who had been giving some very nice insights to the concepts that they have taught. And we thank the NPTEL team for having allowed us to offer this course, and of course the backend team which was trying to help us with recording the video and then editing and then changing the assignment questions, helping us with correcting the errors and a whole lot of stuff. We thank all our NPTEL team, which includes Mr. Avinash, Mr. Naidu, Mr. Naveen, then Ms. Dipali, then Guru Raj Maya and everybody. We also thank the NPTEL chairman at the IISc for having allowed us to do this course. I hope this course was a wonderful journey for you. If there are anything that you want us to improve upon, you could please post it in the forum that we have, the course forum, or probably you could post it even as the YouTube comments. We'll try to look into that and probably improve upon based on your suggestions. On that note, thanks a lot to all of you. Thanks a lot for being a part of this course again. I wish you all the very best on behalf of all the instructors and the TAs of the team. Namaste. Thank you.